Hello, everybody. Welcome to your Wednesday lecture for solid and hazardous waste engineering. So what I've decided to do is to let you peruse the final slides of the recycling lecture. We were close to the end, and so I'll let you look those over yourself. Please let me know if you have any questions. Today, I want to focus on composting and anaerobic digestion so that we have a little bit of time to spend on some problems, and then we'll have a little bit of time for incineration because that does take some time to kind of sink in and to get the real important points. So let's get started. All right. So when we're talking about composting, so as you know, this is a dual kind of process here. We have both composting that we're going to talk about, and then separately, we're going to talk about anaerobic digestion. Both of these technologies can utilize organic material, and they're great ways to utilize it without having to put it into the landfill. So things like our food waste or green waste or any other organic material, we can divert to either composting or anaerobic digestion. And we're going to have a little bit of a comparison here between the two technologies, and then we're going to do a couple of problems or a couple examples here. All right, so introduction, we're going to start with some composting, and you've probably heard of composting before. People do this at home. People do this at like a medium-sized scale for, let's say, even San Diego State University. We have over by our greenhouse on campus, we have a compost pile that we take the food scraps from the kind of daycare facility, and we use those to compost and produce compost. And so people are probably a little bit more familiar with this than anaerobic digestion, but this is also done on a larger scale in particular Miramar. They have a big composting facility there as well. And so you can see that this is done at all different types of scales. So what is it? What is happening? This is a microbial-based process where we have organic material. And so I'll get my little spotlight out here. We have this organic matter of some kind that's being supplied to the compost heap. This organic material is also, if we think of it sort of in terms of biology or chemistry, this is going to be our electron donor. And then we also need to supply oxygen as an electron acceptor. And the way that these microorganisms get their energy is by utilizing the transfer of electrons from the electron donor to the electron acceptor. And I kind of liken it to a windmill where the electrons are being transferred and the microorganisms are turning the little windmill and gaining energy from it. So we need both of those things to be effective. So oftentimes we supply air to supply the oxygen. And then coming out at the end here, we have carbon dioxide and then compost, which is generally, in this case, other than some inorganic or inert materials like sand and so on, a lot of times this is going to be in the form of biomass. Now, what you see here, there's going to be still like some little sticks and seeds and other things that haven't quite degraded. What we're going to do is we're going to sort of ignore that. We're going to focus mostly on the transformation of this organic material to the compost, which is what we can sell at the end. And it's really microbial biomass that is produced that allows for us to have this kind of nice, fluffy soil amendment that we can add and use for fertilization purposes. All right. So with composting, it's, there are some stages or phases, if you will. So there's the mesophilic phase. So this is right at the beginning. This is where, and by the way, mesophilic means sort of moderate temperature liking. So these bacteria, these microbes, they like kind of, room temperature, regular temperature. They don't need to be superheated, right? So these mesophilic bacteria, they get to work first, and they start utilizing these readily available organics. By readily available, I mean ones that are really easy for them to break down. There are other types of organics that have to go through different processes to be able to go into the cells. So these guys kind of are the initial ones that come in, they're at room temperature, they're going to grab the really easy to eat stuff. And so they eat that. And because they're doing all this activity, it actually creates some temperature or some heat, which raises the temperature to about 55 to 80 degrees Celsius. So in the mesophilic phase, you'll see this rapid increase in temperature. Then we have the thermophilic phase. This is where now, the mesophilic phase has raised the temperature to the point where now only these kind of heat-loving microbes can do their processes or, survive and so on. So thermophilic, which means heat-loving microbes, they start to break down the more complex stuff, like the big proteins and the carbohydrates. And we also have fungi and actinomycetes. These degrade some of the more complex compounds like cellulose and lignin as well. So during this phase, this is where the more harder to break down stuff gets broken down. And they can do that because it's at a higher temperature. So this is beneficial to them. Now, after they, eat a lot of their substrate, then we get to the maturation or curing phase. This is where we're starting to run out of nutrients. The microbial activity starts to decline. And then the heat production also starts to decline. So you might see some temperature decline at this point. This phase is where, now the microbes are looking for anything that they can possibly eat. This is where we get a lot of reduction of pathogens because they'll start to cannibalize each other. And we'll get some further degradation of cellulose and lignin. And then it will form these humic and fluvic acids, which are really important for fertilizer. So if you've ever seen a river that's had, let's say it's a little bit of a brownish color, or if you've seen water that's, gone through some leaves and sticks and stuff, and it's coming out brownish, the reason for that color is the humic and fluvic acids. And so these are really great fertilizers. They come from the organic materials, and great reason that we can use this compost, this resulting compost. It typically carries with it the nutrients. All right, so the rate of composting can be affected by a number of things, things like feedstock and nutrient balance, particle size. So the smaller the particle size, the faster our composting will go. It just allows for more access between the microbes and the waste. The moisture content is important. We don't want it too moist, meaning we don't want it swimming in water because then other microbes tend to grow. But we need to have some moisture present, so we need it to be somewhat moist. And so actually in a lot of cases, we may add water to our compost heaps. In fact, the compost heaps that are on campus at the greenhouse, they have pumped in or piped in water pipes so that they can add moisture as needed to make sure that everything's moist. So just like us, as people, we need water, microbes do too, and so we need to supply that to them so that they can do what they do. And then very, very critical is this oxygen flow. So we need to really have enough oxygen that we can allow for the microbes to donate the electrons from the organics to the oxygen as the electron donor. If we don't have that present, then it goes anaerobic, or basically without oxygen, and we start to get a whole different set of microbes there. Things can get smelly. We can have issues. So we really don't want our compost heaps to go anaerobic. And so in order to make sure that doesn't happen, we have to supply enough oxygen. There's a few different ways to do that. We'll talk about that in a minute. So the output of all of this is compost. It's great for, soil amendments. It gives nutrients. In fact, it can help aeration by allowing for kind of more fluffy soil texture that allows for more voids for oxygen to get in. It can improve soil water retention. So all of those voids, they can also fill up partially or fully with water and can help hold that water in place. And then it also helps to combat erosion. So it can be a great soil amendment for areas where erosion is an issue. So now we get into kind of the very, kind of important section of how we calculate, let's say, how much oxygen we need or how much compost we're going to be producing with a certain waste. So let's think about the electron acceptor, electron donor relationship. So microorganisms, when they use a certain electron donor that has carbon in it, it's going to use an electron acceptor, such as oxygen, to take that carbon from that big organic molecule and bring it over, attach it to two oxygens, and produce CO2. So if we have absolute complete oxidation of a carbon-bearing organic molecule, we should get carbon dioxide as a byproduct in the end. So this is kind of how we might balance the equation if we were talking just chemistry. Just chemistry, we would take and balance a half reaction of the electron donor with a half reaction of the electron acceptor, add those together, and get our full reaction. But in the case of microbial growth, one thing that we have to consider is that not all of the carbon goes to CO2. In fact, some of that carbon has to go to biomass synthesis, and with it goes electrons. So what we can say is that when we take electrons from our electron donor, these are the, let's say, one full electron, and a part of that electron will be used for energy generation. This is what uses the electron acceptor. So microbes need both energy and they need, to move around and do what they do, right? But they also need electrons to build up their biomass, meaning reproduce. So they get, this is kind of daily life right here, and then this is reproduction. So they need a fraction of the electrons from the electron donor that it will go to energy generation, which uses the electron acceptor, in this case, oxygen. And then a separate fraction will go towards self-synthesis, or the building of the cells, or reproduction. And this reaction depends on the nitrogen source, which kind of depends on the microbes and so on, but here we can make some assumptions that simplify things. So one thing that's important is that Fe, which is the fraction of electrons from the electron donor that go towards energy generation, and Fs, the fraction of electrons that go towards cell synthesis. If you add these together, they should be 1, right? And it makes sense because let's say 80% go this way. Well, then Fe would be 0.8, and then Fs would be 0.2. So that would mean that 20% of the electrons would go in this direction. And this is important to distinguish because we can't figure out how much microbial biomass is produced unless we understand how much of the electron donor electrons are going towards energy versus cell synthesis. So instead of having a full reaction where we take an electron acceptor and electron donor half reaction and add those together and get a full reaction, here what we're doing is we're sort of adding three different equations together. We have the electron donor reaction, the cell synthesis reaction, and then the electron acceptor reaction. So each of these are half reactions, by the way, and the cell synthesis half reaction is multiplied by your Fs, and the electron acceptor half reaction is multiplied by Fe. So this is our electron donor half reaction. If we look down here, that would be something like this, you know, CHON type of molecule going towards CO2. Oops, this is a little accident here. Should be down here, CO2 and electrons. Now, if we look at our acceptor, our electron acceptor half reaction, it's always going to be this. This is our oxygen half reaction. This is balanced. So we have oxygen, a proton, an electron, and this goes to water. Now, one thing that's important when you're doing this process right here, it has to be 1 electron. So this half reaction right here is on the basis of 1 electron. We would do the same for our RD reaction, and then also for our synthesis reaction, which is already balanced for us. So this is a big, long, nice reaction, but luckily you will be provided with this if you need it. It's not one that's very easy to memorize, so I wouldn't expect that of you guys. But this is one that you would be provided, and it will only be on the basis of 1 electron as well. So I will show you momentarily a little bit more about how we can solve this. But I want to first start with talking about how we get air and oxygen into these systems. So we have different ways of doing that and different methods. So we have what's called an aerated static pile. This is where we have a big pile of our waste. We have a blower that has air diffusers that run across the bottom here. And then this allows these perforated pipes, these air diffusers on the side, to release air into the pile. And that way you don't have to do anything with the pile. The pile just sits there and you're kind of blowing air through the voids to supply the oxygen. Now, if you don't have this set up right here, you may have a windrow setup. And this is where you don't need any of that infrastructure, but you take some equipment and you turn the waste periodically. And what that does is allows for oxygen to get into the voids, and then it gets, you know, as it gets used up, you go back and you keep continuing to turn it so that it has enough oxygen. We also have some in-vessel types. So this in-vessel type right here, this is movement by mixing, meaning that we have waste coming in, we have some sort of mixing in the vessel, and we have this aeration system at the bottom, and then the compost comes out the side. So both of these in-vessel systems are good because they are sort of considered continuous flow, meaning that they're a continuous flow system. There's always stuff going through it. Whereas these two up here are what we consider batch systems, meaning you do one batch at a time and then it turns into compost and that's done. And then you have to start a whole new batch, right? Whereas these guys, there's always waste coming in, it's turning, it's getting oxygen, and by the time it comes out, it's compost. Same thing with this in-vessel silo type. This one, instead, the movement's by gravity. So you put in the waste at the top, it comes down, and there's air supplied at the bottom, and then the compost comes out the side. All right, so that was a really quick thing on anaerobic digestion. What I'm going to do now is that was on composting. Before we get into anaerobic digestion, I'm going to pause it just a moment. And we're going to go to our paper here. And we're going to do an example. All right. Let me see if I can get something going here. Sorry for the delay. You were right there, and wanted to make sure that I have the right example for you all. All right. So what we're going to do, so we have composting, and a lot of times our composting is, and I'll try to make this easy for you to see. I know the lighting's not great, but we have, I encourage you to read through the composting example problem that's posted. But for example, let's say we have an agitated bed of composting that's treating a high sugar waste. And so this sugar waste is going to be represented as C6H12O6. And hopefully you can see that well enough. Let me try to put some better light in there for you. All right. And so the first thing we need to do is we need to get a half reaction for our electron donor. And so we're going to do that by balancing this as our electron donor. This is our sugar. And so I have instructions posted for how to do that, how to balance half reactions. So what we're going to do, very first step that you do is you balance everything except for hydrogen and oxygen. And you do that, first of all, by balancing our carbons with CO2. So we have 6 carbons here. We need 6 CO2 to balance our carbons. Now, if we had nitrogens here on this molecule, which we don't, but if we did, nitrogens are balanced with nitrate for aerobic systems, aerobic compost. Now, when we get to anaerobic systems, we'll have a little bit of a different case, but for this one, definitely aerobic, we would, balance with this. However, no nitrogen. So we've balanced everything except for hydrogen and oxygen, right? We've got 6 carbons and 6 carbons here. So that's the first step. Second step, we're going to balance our oxygens with water. So here we have 6 oxygens, and here we have 6 times 2. So we have 12 oxygens here. So that means in order to balance our oxygens, we need to add 6 H2O to this side, right? So we have over here 6 oxygens, we have 12 oxygens over here, and each water that we're adding has 1 oxygen on it. So if we wanted to balance our oxygens, I think I said that backwards, we need to add 6 oxygens over here. So we'll add 6 waters on that side. So the next step, C6H12O6 plus 6 H2O. Don't worry about the hydrogens at this point. Goes to 6 CO2. So now we've balanced our carbons, and now we have 12 oxygens on this side, 6 oxygens plus 6 oxygens are 12 on this side. So now we're balanced as far as oxygens go. Next step, we're going to balance our hydrogen with protons. And so let's count our hydrogens over here. We've got 12 plus 6 times 2, which is 12. So we've got 24 hydrogens on that side. And we have 0 hydrogens on this side. So we're going to balance it with hydrogens. H plus has 1 hydrogen in each one. So we're going to have to add 24 hydrogens, or protons rather, on this side. So our next step is this, H12O6 plus 6H2O goes to 6 CO2 plus, and we have 24 we need, 24 H plus. Now we have 24 on this side, and we should have 24 on that side. So we should be balanced. The very last thing that we do here is we balance our charge with electrons. So here we're going to look, this is a 0 charged molecule, right? There's no superscript. Same thing with the water. So 0 charge on this side. I think my pen is running out a little bit. Let's switch pens here. This one will be better. And then we have 0 charge around our CO2, and we have 24 times plus 1. So we have plus 24 on that side. And so then we have to think about what we need to do to add. We're going to be adding electrons. Keep in mind, this is a -1 charge. We're going to be adding that to try to make both sides equal. And this is where it can be a little bit tricky. So we have plus 24 and 0. So we're adding a -1. So we have to always add the electron to the more positive side of the two, because it will only reduce our electron or our charge, right? So here, in order to get these two equal by adding a -1 to one of these sides, we have to add 24 -1s to this side, right? So let's do that. So we'll have C6H12O6 plus 6H2O goes to 6 CO2 plus 24H plus 24 E minus. Now this side is 0, and 24 plus 24 negative is 0 total. Now we have a completely balanced half reaction here. However, to use it in the equations that we want, we have to get this in terms of 1 electron. So what that means is we're going to multiply by 1/24 across the entire reaction. So we're going to end up with 1/24 C6H12O6 plus 6/24 H2O goes to 6/24 CO2 plus H plus E minus. This is going to be our fully usable and balanced half reaction. And here we can call this is going to be our RD, or our electron donor half reaction. So if we have this, and let's say we know a few things, like we know that we are going to be using composting, and we know Fe, so this is the fraction of electrons from this donor that's going to go towards energy or energy production. If we know this is 0.8, well, we also know that Fe plus Fs equals 1. So we can solve for Fs as well. And that's going to be 1 minus 0.8, or in other words, 0.2, right? That means that 80% of the electrons are going towards energy, 20% are going towards building cells or cell synthesis. So given this, we already have our RA equation. Our RA equation, if we didn't know it, that's our electron acceptor equation. But if we didn't know it, we could also balance it using the same steps. So we have, make sure you can see this here. All right, so we have O2. And this is what we're starting with as our electron acceptor. Let's balance it the same way we did for the electron donor. So first things first, we balance everything except for hydrogen and oxygen. So that's really nothing that we have to do. And then we're going to balance our oxygens with water. So we're going to take this, we've got 2 oxygens, so we're going to have 2 H2O. Now we have our oxygens balanced. Next up, we're going to balance our hydrogens with protons. So we have 2 times 2, so we've got 4 hydrogens over here. We're going to balance 0 hydrogens over here, so we have to add 4 protons to that side to balance the hydrogens. Now, once we've done that, we have 4 protons over here. We have 4 protons over here. We have 2 oxygens, 2 oxygens. The last step we're going to do is we're going to balance our charge with electrons. So over here, 0 charge around our oxygen. We have 4 times +1, so +4 on this side. So +4 on that side. And we've got 0 on that side because water is not charged. And we have to add electrons, which are -1 charge, to one of these sides. So we're going to pick the side with the more positive charge. So this side, we have to get +4 to 0 by adding -1s. And so we do that by adding in 4 electrons. Now we have this half reaction is balanced, but we need it in terms of 1 electron. So we're going to go ahead and do this 1/4 O2 plus proton plus electron goes to 1/2 water. And now we have our fully balanced and fully usable equation for RA. And this is our RA for any sort of aerobic system like composting. Now you're given the big long equation for the biomass. All you have to do, what we're going to do is we're going to multiply this right here by our Fe. And you're going to multiply that big long biomass equation by your Fs, which is 0.2. And then you're going to have, that means that you're going to have here, let's say 0.8 times 1 electron. And from your big long biomass equation, 0.2 times an electron, and it should be on the same side. So that means when you add those two, the Fe times the Ra plus the Fs times the Rs, you're going to get 1 electron on this side. And we have 1 electron on this side of our electron donor equation. So when we add it all together, all of the electrons should cancel. And what we should get, and I'll give you the final answer here. We'll go to the next page. I'll give you the final answer, but you can also see this in the posted example problem for composting. You can see that we get this very long reaction. It is 0.042, which is C6H12O6 plus 0.2O2 plus 0.0071 NO3 minus plus 0.1714 H2O goes to 0.0071 C5H7O2N plus 0.21 CO2 plus 0.064 H plus. Let's talk about this really quickly. So apologies for the handwriting, doing what's that, a little bit of an angle. So here is our waste, or electron donor, if you will. Here is our electron acceptor. Now, we also need some nitrate in the system. That's along, that's going to be used to build the nitrogen in the cells of the microbes that are growing. A little bit of water is consumed. That's not really important. But then this right here, this C5, I'll rewrite it down here so you can see it well. C5H7O2N. This is our biomass. And so this is a formula. This is used for cells of microbes. So this is sort of a formula that they came up with, that they looked at a bunch of microbial cells, and they did an analysis of how much carbon, hydrogen, and oxygen and nitrogen were there. And then they came up with this ratio, and it's a really good formula to use. And so this is really the cells that are formed. These are the reproduced cells. But this is also, in our case, it's also in our case, our compost that we're going to be selling. So that's really important. The other thing that's important is if we were to be introducing air through a blower, we would have to figure out how much oxygen is needed. And we could figure out, based on the fact that we have 21% O2 in our air, we could figure out, for example, for a certain amount of waste, how much oxygen or how much air would need to be pumped in to satisfy this oxygen demand and produce the compost. So we could also figure out, this is how much CO2 is released, and we could also figure out how much compost right here is produced based on this term right here. So once we have this full equation, we can calculate a number of things that are really important for composting. And so I wanted to show you that, just to give you that quick idea there. All right, so I'm going to move that pen. And we're going to go back to our presentation here, if I can get this going. All right, says I'm screen sharing, so hopefully this is what we are sharing. Okay. So then here we go. So now, okay, so we're quite at the end there. Somehow that went forward. So now we're going to talk a little bit about anaerobic digestion as an alternative to composting. So anaerobic digestion is similar in the fact that it uses microorganisms to sort of eat or consume organic material. And these microbes in anaerobic digestion, they do a number of different things, but essentially the big bulk of what they do is what is called fermentation. Now, fermentation's a little bit different. So, you know, basically microbes love to have an electron donor and an electron acceptor. And in fact, oxygen is their most favorite electron acceptor. Now, if oxygen is not there, they're going to start looking for other electron acceptors like nitrate, nitrite, sulfate, and so on. And they kind of go down the energy list to pick up the most energetic ones first and use those first. And then when that gets used up, they go to the next one and go to the next one. And when they get to a point where they've used up every single possible, you know, external electron acceptor, you would think that everything stops and the microbes can't do anything. But they were pretty ingenious. They came up with this idea, I guess idea, you might say, a way to live or a way to be able to handle that type of an environment. So what they do instead is they have, let's see if we can get this marker in view. But what they do is they have this full, oh, you can't really see it too well, but they have basically one molecule that acts as both electron acceptor and electron donor. What they do is they break it apart into two pieces, with one piece being your electron donor and one piece being the electron acceptor. So they sort of figured out how to make their own electron acceptor out of one molecule by taking it, breaking it apart, one piece being electron donor, one piece being electron acceptor. Then they can have that electron transfer, and that can spin their wheel and basically produce energy for them. So that's essentially in a nutshell what fermentation is. And so these microbes, they use fermentation to oxidize the carbon to CO2. They can do other things like converting acetate, which is sort of an intermediate product, into CO2 and hydrogen and into CO2 and hydrogen and into methane itself. And so all of this anaerobic digestion process kind of proceeds from bigger molecules to smaller and smaller and smaller. And finally, the outputs being mostly CO2 and methane. So in this case, again, not all carbon goes to, you know, CO2 or methane production. Some does go to biomass synthesis, but it's significantly lower than in the aerobic processes. So with the aerobic processes, they get a lot of energy by using oxygen as their electron acceptor. Here, you can imagine they have to first expend a lot of energy to produce enzymes that go outside of their cell and break apart these molecules. And then they can get a little bit of energy from the electron donor and acceptor that they've produced. And so because of that, they really don't get a whole lot of energy out of this. They have to do this reaction multitude of times before they get enough energy. And it also means that they're not really freeing a whole lot of electrons for themselves. And so they don't have a lot to spare for their biomass synthesis. So that means that they're a lot slower growing just because they don't have that really energetic ability to use oxygen as their electron acceptor. So what comes out of anaerobic digestion? A mixture of kind of this biosolids in terms of biomass liquid. So usually the biomass is suspended in the liquid. And we get this biogas, which is a mixture of CO2, methane, and some trace gases like hydrogen sulfide and so on. But what we're really after here is this methane, because they're producing methane. We can burn that methane, goes back to CO2, but we can use that as a fuel. Now, CO2 we can't burn, so often we have to do some sort of cleanup of our biogas or removal of CO2 or upgrading and so on. But this methane is what we're after. And so in this case, instead of really getting a compost that we go and sell for profit, here we get methane that we can use as energy. So it's either compost, which is more fertilizer based and nutrients, or we get more of methane as energy recovery. Now, some people do use these biosolids as sort of, because they are microbial cells, so they can land apply these in certain conditions for crops, but oftentimes they haven't had a lot of pathogen removal in anaerobic systems, so they typically won't apply this biosolids to crops that are going to be eaten by people. So, maybe alfalfa for cows or something like that, but not really food crops without additional processing. So anaerobic digestion, because, it is this kind of long, lengthy, multi-step process, it, does take a little bit of time. And in fact, the very first process in this, or first step in the anaerobic digestion process is what we call lysis, L-Y-S-I-S. And what that means is that they're basically taking these big molecules and they're breaking them apart. And they're not getting any energy or anything out of it. They just have to do that to prep these molecules to start then doing the fermentation process. So that process, it can be pretty slow. So some of the things that we like to do for pretreatments to speed that process up are things like physical pretreatments, like mechanical treatment, thermal, even microwave has been used, and biological. So we might have kind of these two-stage or enzymatic type of systems where we sort of pre-treat the material so that it will break down a lot quicker in the anaerobic digester. Another thing we have to consider is inhibition. So we can have ammonia, which is inhibitory. That's produced from pretty much most nitrogen that goes in as part of the feedstock. So if you have nitrogen attached to your waste in some form, it's going to most of the time turn into ammonium. And if that gets too high, then that can inhibit the methane production process, which is really the goal of the anaerobic digestion process. We also have to be very careful about low pH. So methane won't be produced if we have too low of a pH, so lower than 6.5 or thereabouts. And part of the reason we can run into that issue if we give too much food to overload our anaerobic digester, the microbes can't break it down fast enough, and we start to get these intermediate products, which are called volatile fatty acids, or VFAs. And they're volatile fatty acids, but they're acids at heart, and so they can decrease the pH if they build up. So we can't have a buildup of these intermediates. We need those to be consumed just as fast almost as they're being produced, so that we don't get this buildup and we don't get a low pH and we don't stall the methane production process. So we can get kind of what we call stuck digesters if that happens. So here are the processes. So we start with these really complex organic compounds, big carbohydrates, proteins, and fats. And this is the process that does take a while. It's this hydrolysis process. And this is really what we're targeting when we do pretreatments for anaerobic digestion. We're trying to speed this process up. And so then once we have kind of those big molecules broken down, we have sugars, amino acids, and fatty acids. Then we can start with these different groups of microbes that start to do this step, which is acidogenesis. So you can think of this acid and genesis means it's generating or producing acid. So acidogenesis means producing acids, these organic acids. And this is where if we allow these to build up, we tend to get too low of a pH and we can stall our system. So we need everything to be working very well together. After we've produced these, we can take those and do acetogenesis. And so aceto refers to acetate, and genesis, of course, is production. So we're producing acetate. At the same time, we're producing some hydrogen and CO2. Now, these can be interconverted, but then the real point that we're trying to get to for anaerobic digestion is this methanogenesis. Again, methane production. And so here we can either take acetate and produce CO2 and methane. So in fact, acetate has 2 carbons in it. One of the carbons will produce a CO2 and one of the carbons will produce a methane. And that's what happens in this acetate production. Alternately, we can have hydrogen and CO2 that are combining. In this case, we only get methane. So here, this is only going to be only methane. I'll move this over here. And then over here, we'll get CO2 and methane produced. So these two are different routes. We have 2 different types of what we call methanogens that do this. And so they end up producing, we have more acetate production or acetate conversion into CO2 and methane than we do hydrogen and CO2 into methane. So because of that, we end up with this biogas that has a mixture of CO2 and methane. All right. So I won't get into this too much. This is something I found interesting. It just goes over how you can use anaerobic digestion along with other processes to be able to do things like produce biodiesel, biochar, heat electricity, fertilizer. So this is really kind of like a biorefinery system, but it all starts around this anaerobic digestion. So there's a lot you can do with it beyond just the production of the biogas, which has CO2 and methane. So there's 3 types of methane producing microbes. There's the acetoclastic methanogens. These guys, as I mentioned, they take acetate and take one of the carbons from acetate and make CO2 and the other carbon and make methane. In this case, CO2 is both a product and an electron acceptor. So it's in a way balanced the same way as you would a redox reaction. Now, hydrogenotropic methanogens, these guys take CO2 and hydrogen and produce only methane, so they don't produce any CO2. And one thing to note with these guys is they participate in what's called direct interspecies hydrogen transfer or electron transfer, sometimes called diet. And what is interesting about this is that they allow for the earlier steps of fermentation to happen. So some of those steps of fermentation are not thermodynamically feasible unless it's a fermentation process that's producing a little bit of hydrogen on this side. And as written, it's not thermodynamically feasible. However, if you've heard of Le Chatelier's principle, that means that if you lower the concentration of your product. So if you have a reactant going to a product and you lower the concentration of the product, then it pushes the reaction forward, right? So it tries to kind of rebalance. And so if you remove all the product, it's going to restart and the reactant is going to move towards generating the product. Le Chatelier's principle. However, in the system of an anaerobic digester, the fermentation process itself, in some cases, is not thermodynamically feasible unless you remove that product hydrogen to such a low level that it pulls or pushes the reaction forward into producing more hydrogen and doing more fermentation. So what these guys do, they eat up this hydrogen very, very, very fast. And they do that very, very close to, so they associate with some of these fermenters. So they're really right next to each other. So that when the fermenter produces hydrogen, these guys can just snap it up and reduce it to such a low level that now the fermentation can continue because the product is at such a low concentration because these guys are doing this right here. So they're really integral towards pulling or pushing fermentation forward and making it thermodynamically feasible. These methylotropic methanogens, I mention them just because they are typically a third group of methanogens. They can take things like methanol and convert it to CO2 and methane, or they can take methanol and hydrogen and produce methane only. These guys are kind of more minimal in the scheme of things. And so often we focus more on these two types in anaerobic digestion. All right, so here is an anaerobic digestion problem. And so a couple of things here, if you're not familiar with this terminology, first we want to calculate this hydraulic retention time. And this is considered how long one molecule of water will stay inside the digester. So the digester is, if it's a continuously stirred tank reactor or CSTR, that means that it's, the water is going in with some of the feedstock and then being mixed around and then eventually leaving. Hydraulic retention time is basically how long it stays inside the digester. It also means that's how long this digester has to break down the material. Assume the digester is operated at steady state. We can write the mass balance for this. And then we can calculate a steady state organic concentration. And then finally, if we need to change the output to be 2 grams per liter, what would our new flow rate be? I think I'm going to pick this one up on Monday so that we can do this all together. So bring your calculators, bring some paper, and we'll try to work this one through. All right, so in closing, we want to compare our anaerobic digester with our composting system. We can compare it based on feedstock. It can be the same feedstock for both. Both achieve volume reduction. However, anaerobic digestion typically reduces the solids a lot more than composting, because composting, remember, those microbes can produce a lot more biomass using oxygen as their electron acceptor. Also, the process condition, this is very different. So we have aerobic conditions, meaning we need to supply oxygen in some form. And then for the anaerobic digester, anaerobic, meaning we need to exclude oxygen and typically all other electron acceptors. For preparation, sometimes composting, we might add a bulking agent ahead of time, just to allow for more moisture to be held in there, maybe to allow for more pore spaces so that we can supply more oxygen and have it be held inside there until it's used. So sometimes you might add a bulking agent to composting. And then anaerobic digestion here, we're trying to do pre-treatments to really break down those big complex molecules into smaller molecules that the microbes can actually consume. And then, of course, our products here, we have compost that we can sell for fertilizer purposes or soil amendments. And then here we have biogas and biosolids. The biogas we can get energy from by using the methane that's produced. And then the biosolids, in some cases, we can use this for fertilizer as well. All right, so that is anaerobic digestion and composting in a nutshell. We're going to meet again on Monday, and we'll work through the anaerobic digestion problem, and then I'll answer any questions that you might have about balancing half reactions or the composting reaction that we need to develop. But I encourage you to look at those examples that are posted, and then we'll start talking about incineration and go from there. So have a great week, everybody. Look forward to seeing you all on Monday. Bye-bye.